In this video, we're going to take a look at some circle proofs. In this first example, we're given circle O. DB is tangent to the circle at point B. BC and BA are chords. And C is the midpoint of arc AB. And what we're trying to prove is that angle ABC is congruent to angle CBD. So we're trying to prove that these two angles are congruent to each other. First, let's start with the given information. We are given that C is the midpoint of arc AB. So that means that arc AB is being split at C into two equal arcs. So that means arc AC and arc CB are both congruent to each other. Angle ABC is an inscribed angle, and inscribed angles are half of their intercepted arcs. And the intercepted arc for angle ABC is arc AC. Angle CBD is an angle on the circle whose vertex is on the circle, and those work the same way as inscribed angles, where they're half of their intercepted arcs, and the intercepted arc for the angle on the circle is arc CB. Since both of those angles are half of their intercepted arcs, and both of their intercepted arcs are congruent, the angles need to be congruent as well. For example, if these were both 100, these would both be 50, just making up numbers here. Now let's put this into a proof and see how this would be written up. For this video, I'm not going to write down the givens, just because I don't want to take up a lot of time on the video and a lot of space here, but I'm going to make a spot for it because you should always start off with your given information and all of your given information. The first thing that we did when we were talking about this example is we said that arc AC is congruent to arc CB. And the reason for that would be a midpoint splits an arc into two congruent parts. Then we said that angle ABC is an inscribed angle, so it's equal to half of its intercepted arc AC. And I'm going to put Y over here. Inscribed angles are half their intercepted arcs. And then we talked about how angle CBD is also half of its intercepted arc, which is arc CB. And I'm going to put here angles on the circle are half their intercepted arcs. And since arc AC and arc CB are congruent, that means that arc ABC and arc CBD need to be congruent. Technically, since we already stated that AC and CB are congruent arcs, we can just write substitution. But I'm going to write it out in words so it's a little bit easier to see. Angles that are both half of congruent arcs are congruent. But once again, I could have just wrote substitution because I already indicated that the two arcs were congruent. And so then if they're both half of congruent arcs, then by substitution, the angles are congruent. But I wrote it out in words so that way we could see why. In the next example over here, we have that PA and PB are tangent to circle O. We have that OA and OB are radii of the circle. And we have that OP intersects the circle at C. And what we need to prove is that angle AOP is congruent to angle BOP. these two angles are corresponding angles of the two triangles. So what we need to do here is prove the two triangles congruent, and then we can use CP/CTC to say that the corresponding angles have to be congruent once we already have proven the triangles congruent. There are multiple ways to prove the triangles congruent here, so I'm just going to mention one way in my proof here. And I'm going to end up using HL, just so you can see how it's written with HL, but there are other ways that you can use. For HL, I need right angles, and we're going to get right angles because we have a tangent to the circle and we have a radius. And when a tangent to a circle and a radius intersect, they intersect to form right angles, and that's happening on both sides in both triangles. I also have a shared side between the two triangles. So OP is congruent to itself by the reflexive property. And then I do need one pair of legs. I can use this pair of legs because all radii of a circle are congruent. Or I can use this pair of legs. I can put the same marking. Or I can use this pair of legs because two tangents to a circle from the same outside point are congruent. Either one works. Once again, HL is not the only way to do this proof. I'm going to write up my proof so you can see how this looks. Once again, I am not going to write down the givens just to save some time and space in the video, but you should always start off by writing all of your givens. I'm going to write that angle PAO and angle PBO are right angles when a radius and tangent intersect. They are perpendicular and form right angles. So now I can say that triangle PAO and triangle PBO are right triangles because a triangle with a right angle is a right triangle. And that's needed for HL because I know from planning my proof that I'm going to be using HL. And for HL, you do need right triangles. So that does need to be stated in your proof that you have right triangles. Then we talked about how OP was congruent to OP because of the reflexive property. And then we had that AP was congruent to BP because two tangents to a circle from the same outside point are congruent. So then we can say triangle PAO is congruent to triangle PBO by HL. That's the method I used here. Once again, not the only method, but it's the one I used. And then I can say that angle AOP is congruent to angle BOP due to CP/CTC because we already proved the triangle's congruent. So then the corresponding angles are also congruent. In this next one, if I take a look at the proof statement first, I see that I'm proving a product. And when you're proving a product, it's the same 3 steps every time. We're going to prove the triangle similar, and it's always going to be by AA when we're doing a 2-column proof. Then we're going to prove a proportion because you need a proportion so that way you can cross multiply it to prove the product in your proof statement. So that's going to be the ending of our proof. Prove the triangle similar, prove the proportion, and then prove a product. So I just need to figure out where I'm going to get my 2 congruent angles from. The first one's pretty straightforward. We do have intersecting lines here. So we do have vertical angles. Oops. And then we do have inscribed angles. For example, angle ADE is an inscribed angle that intercepts arc AC. And angle, let me do it in a different color, angle CBA is an inscribed angle that also intersects arc AC. Two inscribed angles that intercept the same arc are congruent because if the arc is 100 and they intercept the 100-degree arc, then they both have to be half of that, which is 50. So inscribed angles that intercept the same arc have to be congruent. So I'm going to use angle ADE congruent to angle CBE. You could have used the other pair of inscribed angles, angle A and angle C, and that would have been absolutely fine as well. Now I'm all ready to write up my proof. Once again, I'm going to save some space and some time in this video, and I'm not going to write the givens. Now let's move on to our vertical angles. So angle AED, be careful to name them with 3-letter names. You can't call them angle E, is congruent to angle CEB. And that's because intersecting lines form congruent vertical angles. And then we have that angle ADE is congruent to angle CBE. And that's because inscribed angles that intercept the same arc are congruent. And that's our 2 A's for AA. Here's 1 A and here's our second A. So now we can say that triangle AED is similar to triangle CEB, and that's by AA. And now we can prove a proportion involving the segments from the proof statement. So just put the segments from the proof statement into a proportion and then see if they cross multiply to give you the product that you need. And if they don't, then you need to adjust it. Let me check mine. Oh, that doesn't cross multiply correctly. AE times ED, but it's supposed to be AE times EB. So let me swap that around. That should be EB. And then if I'm multiplying this way, it should be CE times ED, not CE times EB. So let me make that adjustment. So always just double check. And now we can write our reasons. It's the same reason anytime you're proving a proportion, because you just proved the triangle similar. Similar triangles have proportional corresponding sides. And anytime you're proving a product, it's the same reason. It's a fancy way of saying cross multiplying the proportion. In a proportion, the product of the means equals the product of the extremes. Moving along, we have quadrilateral ABCD inscribed in circle O. We're told that AB is parallel to DC, and diagonals AC and BD are drawn. We need to prove that triangle ACD, that's this triangle over here, is congruent to triangle BDC. That's this triangle over here. Anytime we have overlapping triangles, you should draw them separately so that you can see what belongs to each. So the blue one is triangle ADC. Let me relabel that. And the pink one is triangle BCD. And already I can see that they share DC. I'm going to put an X on it for reflexive property. And if you look at the separated triangles, it's the same 2 letters, C and D. So that means that they share that side in common. So that already gives us a side to work with. We do have parallel chords. And when we have parallel chords intercept congruent arcs. So the arcs in between them are going to be congruent. So arc AD in arc BC, the arc connecting the two parallel chords are congruent to each other. And remember, congruent chords intercept congruent arcs. So if we have congruent arcs, the chords that intercept them are congruent. So AD and BC are congruent. So we're doing great so far. We already have two pairs of sides. If we can get another side, which I don't think we can do here, that would be good. Or if we can get an angle, specifically if we can get angle ADC and angle BCD so that we can have side angle side. Angle ADC, this angle over here is an inscribed angle, and its intercepted arc is arc AC. And angle BCD is this angle over here, and its intercepted arc is angle DAB. But those have to be congruent because DA and BC are congruent. So if they both have AB as part of their intercepted arc, then let me write it out. So for angle ADC is half of its intercepted arc. And its intercepted arc for ADC is arc AC, which is AB plus BC. That's arc ABC, its intercepted arc. And arc BCD, angle BCD is half of its intercepted arc. And its intercepted arc is arc DAB, which is arc DA plus AB. But this is the same. And these were congruent arcs, so this is the same. So the measurements of the angles are the same as well. So let's write this down into a statement reason chart, and that gives us side angle side. I'm going to need more space for this one, so I'm going to continue next to it afterwards. Let me write here given. So I'm going to write arc AD is congruent to arc BC. And that was because parallel chords intercept congruent arcs. And then we said chord AD was congruent to chord BC. Congruent chords intercept congruent arcs. We also had DC congruent to DC, and that was the reflexive property. And now we just need to say why angle ADC and angle BCD are congruent to each other. So I'm going to actually write out everything that we had. So first I'm going to write that arc AB is congruent to arc AB because that was used in what we did before. And that is also the reflexive property. And then I definitely want to use addition here. So I'm going to write, let me start with the arc that angle ADC intercepts. So let me start with arc ABC. That's arc ABC. And then after that, we'll do the arc that angle BCD intercepts, which is DAB. Okay. So in order to use addition, we have to start with congruent. So I'm going to start with AB on both sides. And then you have to be adding congruent. So AB plus AD. Let me get a little bit more space here because I'm running out of space. Is congruent to AB plus BC. And we already established that those are congruent. So we can do this because of addition. And then due to substitution, arc AB plus arc AD is arc DAB. And then arc AB plus arc BC is arc ABC. And then that's substitution. So now I can say that angle ADC is congruent to angle BCD because inscribed angles that intercept congruent arcs are congruent. And now I'm done with the proof because all I have to say now is triangle ACD is congruent to triangle BDC, and that's due to side angle side. This one was quite tricky here. Here's another one, and we're going to do 2 more for this video. In the accompanying diagram of circle O, AD is a diameter with AD parallel to chord BC, and chords BD and AC intersect at E. Prove that BE is congruent to CE. So here's BE, and here's CE. So we need to find what triangles we can prove congruent, so that way we could CP-CTC those 2 segments. So I'm going to try for these 2 triangles to prove these ones congruent. I already have the vertical angles, and since we have parallel chords intercept congruent arcs, so arc AB and CD are congruent. And then when you have congruent arcs, the chords intercepting them are congruent. So chord AB and chord CD will be congruent to each other. We also have parallel lines. So I'm seeing if we can use alternate interior angles, but it doesn't look like we can use alternate interior angles here with these 2 triangles. So we might want to use a different pair of triangles in order to prove the triangle's congruent. We also do have a diameter. I'm just seeing if there's anything else that we can figure out here, because sometimes it takes a minute to figure it out. And there we have it, because we do have a diameter. So sometimes when you can't figure out where to go, look back at the given information, see if it can help you. So if I take a look at this angle over here, angle ABE, angle B, angle ABE opens up or intercepts the diameter, so 180 degrees. And since it's an ascribed angle, that means that this is going to be 90 degrees. And same thing for this angle over here. It's an inscribed angle that intercepts the diameter, a semicircle. So it's also going to be 90 degrees. And now we have angle side. So now we're all good to go. So I'm going to start writing my proof. And once again, to save some time in this video, I'm going to skip writing down all the givens. We said that arc AB was congruent to arc CD. And that's because parallel chords intercept congruent arcs. We also had that chord AB is congruent to chord CD. And that's because congruent chords intercept congruent arcs. I'm going to put the vertical angles in. So angle BEA is congruent to angle CED. And that's because intersecting lines form congruent vertical angles. And now I'm going to put in the right angles. angle ABE and angle DCE are right angles. Inscribed angles that intercept a semicircle are right angles. And since we're going to use angle side, we need congruent angles. So angle ABE is congruent to angle DCE. And that's because all right angles are congruent. And that gives us the two triangles ABE and CDE. Let me do DCE instead. Are congruent to each other by angle side. And then we know that segments BE and CE are congruent by CBCDC, because once the triangles are congruent, then the corresponding sides are also congruent by CBCDC. We have one more proof for this video, and I'm looking at the proof statement, and we're proving a proportion. So our first step is going to be to prove the triangle similar, and when you're doing a similar triangles proof, it's always going to be AA because we don't have numbers, so we're only going to be able to find angles, not proportional sides, and then we're going to prove the proportion. So in the two triangles, I do have to look for AA. We have tangent EC drawn to diameter AC. So I already know that when a tangent and a diameter meet, they form a right angle. Let me see if I can get a right angle in the other triangle. I see that angle B looks like a right angle. It's an inscribed angle, and it's an inscribed angle that intercepts a semicircle, half a circle, because AC is the diameter. So that would be a right angle as well. And then we're told that chord BC is parallel to secant ADE. Oh, so we can use the alternate interior angles. And there we have it. That's our whole proof. So let's write it up. Okay, I'm going to start with the right angles. So I'm going to write down first that angle ACE is a right angle when a tangent and diameter intersect. They are perpendicular and form a right angle. I'm going to do the other right angle next, angle ABC. Angle ABC is a right angle. An inscribed angle that intercepts a semicircle is a right angle. And then we do need congruent angles for AA. So I do need to say that the two right angles are congruent to each other because all right angles are congruent. Okay. Now the alternate interior angles. Angle BCA is congruent to angle CAE. Alternate interior angles are congruent when parallel lines are cut by a transversal. And that's pretty much the whole proof. Now we can say triangle ABC is similar to triangle ACE by AA. And then we can end the proof by proving the proportion that we need to prove. And our reason is the same anytime you're proving a proportion. Corresponding sides of similar triangles are proportional.